Okay, in this video segment, we're going to talk about fission and fusion and those two different nuclear processes. So we'll start here with fission, and to start off, we're going to watch a little video.
Binding energy per nucleon reaches a maximum at a mass of about 56. Larger nuclei become more unstable as the mass increases. Very large nuclei, such as uranium-235, can split when they are hit by high-energy neutrons. In nuclear fission, a large amount of energy is released, and two smaller, more stable nuclei, such as barium-139 and krypton-94, are formed.
So if you take a look at what happens here, we start off with something like uranium-235, a very, very large nucleus of a very big atom. And if we bombard it with a neutron at high enough speed, we can split that. Now that splitting process actually creates two smaller atoms, creates more neutrons, and it creates a lot of excess energy. Okay, that energy comes from a mass deficit. So we're not actually like transferring energy here, transferring mass here. This is actually a true reduction of mass, meaning the mass is now gone, and it converts into energy. And that equation for Einstein's E equals mc squared is how we actually can calculate that. We won't do it in here, but it's how you could calculate it. Okay, so unlike the rest of the chemistry world, this is a true loss of mass and gain of energy in this process. Okay.
Additional neutrons are also released. If a critical mass of uranium-235 is present, then most of the released neutrons are captured by other uranium-235 nuclei, and a nuclear chain reaction results, as can be seen in this animation. The energy from nuclear fission reactions is harnessed in atomic bombs and in nuclear reactors.
Okay, so that's fission. We're taking something really big, splitting it into smaller things, and then it generates more neutrons to keep doing it. Okay, the things that we use in our world are uranium-235 and plutonium-239. They are the most fissionable and most efficient of our atoms, but they don't come very pure. So if we take a look at a simulation here of this process, and we're going to go to this idea of a chain reaction. So if I start with a whole bunch of uranium-238 and a very little uranium-235, because that's how we would mine this or get the ore, is mainly uranium-238, the stable isotope. 235 is the unstable isotope. And I fire a neutron into here, well, it hits a 238 and that just absorbs it. Nothing happens. Okay, so it doesn't work really well when you have uranium-238 anyway. So now we got a little bit of a chain reaction, but then it stops. So we have to purify our uranium, so it's almost all uranium-235. Okay, and when it's almost all uranium-235, and we get a critical mass or a purification of that, and then we send a neutron in, we get a really nice nuclear chain reaction where they explode, they split, little things go flying off, and tons of energy comes dumping out. Okay, now that would be a simulation like a bomb would work, okay, where we do not control it. We let it go, we actually get the thing started, and just naturally it's going to run almost instantaneously through this very aggressive chain reaction. In a nuclear reactor, which are fission nuclear reactors, and all of our nuclear reactors that produce energy are fission-based ones, by the way, it's still the same reaction. We're still just sending a neutron in, and we're letting it purify uranium-235. This is all little green dots and rods. These are all purified uranium-235. These are called fuel rods inside a nuclear reactor. And we can't really speed them down or speed them up or slow them down in terms of the chemistry. All we can do is get in the way. Okay? So in this case, you start a reaction. You can actually open this up and you fire a neutron in there, and it's going to start reacting. And then I can use control rods to come in here and block the process or slow it down. Okay, and if it slows down too much, I can open it back up and I can slow it back down again. So the idea is that we actually control the chain reaction, not by changing the chemistry or warming it up or cooling it down or pressurizing it. We actually have just blockers in the way. Okay, these are called control rods. These are made of material that absorb neutrons without chemically splitting, without reacting. So they're a material that can absorb neutrons and keep it running. Okay, so one of the issues or tricks to a nuclear power plant is making sure these control rods are always right in terms of movement, that is physical movement, so you get our power output and the energy you want. But you can't let it get too hot. If it gets too hot, you can melt down a nuclear reactor, and that has happened in a couple cases in our history. Okay, so taking a look at this idea of fission, kind of the take-home message here. Fission is the splitting of the atoms. Okay, you have to be really big. All right, you have to be above the size of iron to even be chemically possible to be split, okay? And then the bigger you are, the more likely it is, okay? So it puts out a ton of energy for us to work with. Now, here's another image of that, okay? So you kind of see that chain reaction where, 1 goes to 2 to 3, and chain reactions as its way through. Just kind of get another visual about how that kind of would work, okay? Take a little image of a nuclear reactor and what it is. And we talked about that a little bit already, but here's kind of a more diagram of what a nuclear reactor really is. So at its core, you have the reactor, and inside of here you have your control rods controlling that fission reaction. And all this is really doing is we're just generating heat, okay? That's all we want to do is generate a bunch of heat. We pump water through that. That generates steam here. The steam then runs a turbine, and the turbine generates electricity. And then we have big cooling towers do that. So all these gigantic towers you see on these like things about nuclear reactors or nuclear power plants, all they are is cooling water. They're not even part of the actual reactor. So it's interesting. The reactor core can fit in like a normal classroom. Okay, so if you actually were inside a nuclear reactor, we could fit the entire core of that in our classroom. That's how small they are. It's just all the other stuff they do for safety and water and steam and cooling it is what make those power plants so big. And they also have multiple cores too as they do that. Okay, so now there is a possibility of some waste and accidents here. So one of the drawbacks of fission power is the fact that the rods left over, those fuel rods left over, once they're not usable anymore, they still radiate heat and they're still radioactive for decades upon decades. So they have to store them. Okay, so they store them in like deep tanks with water to absorb that heat energy for over 10 years. And they continue to react as they do that. So they have to shield the reactive material. Once the plants are full, or they have to move the stuff off site, and they have to bury it in deep underground kind of places to put them. And they bury them deep down and they encase them in concrete, and they just sit down there and radiate heat until they cool down, hundreds of years later. You can imagine nobody really wants a radioactive waste dump in their backyard, so it's kind of tough to deal with that. Plus, if you don't seal it right, you could have leaking of radioactive material, which could be an environmental hazard for sure. Okay, there are other types of radioactive waste. It's called low-level waste versus high-level waste. This is just things you get from like medical, okay, like X-ray film and that kind of stuff. Or other isotopes that they use in tracing things in medical worlds. So these things can be buried in certified landfills. The landfill just has to have gone through a process of knowing how to bury that stuff and seal it off to keep it safe. Okay. Is there some controversy of this? Of course there is, right? Radioactive material we know causes cancers, causes environmental issues. So anytime you have an energy source that can also cause problems with your world and your environment, there's going to be some controversy with that. So part of your job as a growing citizen is to kind of think about that and weigh the pros and cons of that. So what is it better to have a coal-fired plant that's pushing a lot of waste and like pollution into our air, or is it better to have a nuclear power plant? Which one do you think is better for our environment? Okay, now ideally we'd have neither, right? We'd have something that produces energy that has no waste that can be harmful. So that brings us to fusion, and in fusion we're actually looking at the exact opposite process as we are fission. Okay, in fission, we had really big atoms that we split into smaller ones. In fusion, we start with really small ones, and we combine them together to make bigger ones. Okay, in both cases, they generate excess energy. So very much like fission, where that process had a mass deficit, fusion also has a mass deficit, and it releases a bunch of energy. Now, the benefit of fusion over fission is that fusion creates stable atoms and doesn't create anything that is radioactive. So if we could create fusion reactors and use those to power our world, we would have a very, very, very safe way of generating energy. The problem is fusion reactors right now, we do have them. They do exist in our world. They just actually use more energy than they output to get them to work. They just need to be way too hot, basically, for us to make it handle in our world. But the technology is increasing every single year. All of the major superpower countries are researching this. And there is potential that we could get a fusion reactor that could become something that is usable in the future. We'll see how the research goes. Okay, we obviously have fusion in our solar world. Okay, so all of our stars, all of our suns, they use fusion, and we also have fusion bombs too. So fusion bombs do work because it turns out we can create a lot of energy and a lot of heat real fast in a small space to allow fusion to happen as a bomb, but we can't control it yet. That's kind of our problem. Okay, so fusion has to happen with small things, and iron's like your limit to that in terms of how it can be fused, but fusing things, the bigger they are, the harder and harder it actually gets to work. Here's a little video on how fusion works.
Binding energy per nucleon increases up to a mass of about 56. Smaller nuclei can become more stable by fusing with other small nuclei. Two naturally occurring deuterium atoms can fuse to form helium-3 and 1 neutron. A large amount of energy is given off in the reaction. One tritium nucleus and one deuterium nucleus can fuse to form helium-4 and 1 neutron. The second reaction is favored for experimental nuclear fusion reactions because less energy in the form of heat is required to initiate fusion.
So you notice how very small these are. We're talking about individual hydrogen isotopes, individual helium isotopes, the smallest of our atoms, is what we're using to try to make fusion happen in our fusion reactors. Okay, even in the sun, that's what it uses. It uses hydrogen and helium to actually power our stars, those kind of things. Okay, so kind of a take home: fission is splitting of big atoms to generate energy. Fusion is the combining of small atoms to create energy. Both would run uncontrolled if we could get them up to the right temperatures and the right number of neutrons in there to cause it to happen. Fission is our source of nuclear power that we have right now. Fusion and fission are both used for atomic weapons, and fusion hopefully will be something that we can have as a power source if our technology continues to improve and gets better.